Now let's talk about coordination number and the geometries of coordination complexes. The coordination number tells you how many atoms are attached to the transition metal, or how many bonds there are to the transition metal. This does not necessarily mean the same thing as how many ligands are attached to the transition metal. Let's take a look at some examples. So we're going to look at our complex that has cobalt as our transition metal, 6 NH3 ligands, and we have 3 chloride counterions. This is what the Lewis structure of this might look like. And if you were to determine what the coordination number is here, you would say that it's equal to 6 because you have 6 bonds to the transition metal, right? We're not counting the stuff that's part of the counterions. We're only counting the things that are inside of the coordination complex ion. Now, in this case, the coordination number is equal to the number of ligands that you have because all of the ligands here are unidentate. But these numbers will differ when you're dealing with bidentate, tridentate, hexadentate ligands. So now let's take a look at a complex ion where we have cobalt as the transition metal. We have 2 ethylene diamines, which are bidentate ligands, and then we have 2 chloride ligands. We also have a Cl at the present as a counter ion. So this is the Lewis structure of this. And in the Lewis structure here, what I'll say is that this point here and this point here represent carbon atoms. The same here and here. This represents a carbon atom. This represents a carbon atom. Now, in the case of this complex, we still have a coordination number of 6 because even though there are only 4 ligands attached, 2 of them are ethylene diamines and they attach twice to the transition metal, right? We have 1, 2, 3, 4, 5, 6 total bonds to the transition metal, so the coordination number is still 6. Determining the coordination number helps you to determine what the geometry of the complex will be. Let's take a look. So if you have a coordination number of 2, then you're going to have a complex ion that has a linear geometry. An example of that might be if you have silver with 2 ammonias as your ligands. For a coordination number of 4, you can have one of 2 cases. You could either have a tetrahedral geometry or a square planar geometry. And it's not always so straightforward to be able to predict which one it is when the coordination number is 4. So when the coordination number is 4, you'll be told whether the geometry is square planar or tetrahedral, if that is relevant to the question. When the coordination number is 6, then the geometry will be octahedral in every. That brings us to the end of this discussion, and next we'll begin talking about crystal field theory.